we're going to talk through how you might go about preparing a formal report for a project. So the context for this is the computational physics course that I teach, where you have a mini project which lasts about 6 or 7 weeks, and at the end of it you're expected to return a report which is between 10 and 20 pages long. And I think that a lot of people have some problems with working out how to go about this, so I thought I'd just talk through it. So we're going to start here. This is a generic word processing program. I'm sure you can work out which one it is. You're welcome to use this kind of thing or a typesetting program such as LaTeX. My advice would be that you concentrate at the beginning on the content, i.e. the words and some basic figures and the layout, rather than worrying about how you lay it out. That can come later. So here we are. We've started with a completely blank piece of paper, a completely blank report, and I'm going to talk you through the general process that we would go through in preparing a report. To do this, I've got an example of a project from the previous year. Obviously, I'm not going to go into full details. So the most important thing at the beginning of writing a report actually is to think about the overall structure and the basic content. So obviously you're going to need some kind of title, you'll need an author. This kind of formatting is entirely trivial. Obviously we'd go back and center them and make them big and this kind of thing. Do we want an abstract? That's an interesting question. It's generally done in scientific papers, but it's not a requirement. The point of an abstract is to give an overview of what's going on in the report. So you can put that in there, but I would say write it at the very, very end once you know everything that's in the report. After that, I think the most important thing that you can do is to lay out the section headings. So let me see if I can actually work out how to do this. No, I can't do that because I hate this kind of program. So I'm just going to use standard boring plain text. And I'm going to say my first section is going to be an introduction. This is now turned into a numbered list, so the overall layout is going to look horrible, but this is actually quite an important point. It doesn't matter how it looks at the moment, so long as you can see how the information flows. I've started with an introduction. That's because that's the standard way. After that, well, we often will have some kind of methods section, we will have some kind of results section, and we will have some kind of conclusions. So that's the general outline. My suggestion is that actually what you do is you put in those kind of basic sections and then start thinking about subsections, and then think about what you want to put into the subsections in terms of figures or bullet points to indicate the paragraphs. But for now, let me just introduce you briefly to the project I'm going to be talking about. So this is a project which is based on fluid flow. So here are the famous Navier-Stokes equations. So this second one actually is the continuity equation, and the first one is the Navier-Stokes. V here is the velocity of a fluid, and this is possibly the most famous example of a completely insoluble problem. We have no idea how to solve this, and I think there's $1 million prize if you do manage to do so. What we can do is we can make approximations and explore properties. So we can't do a general solution, but we can make an approximation. So in this approach, we're thinking about steady state, two-dimensional, incompressible flow. So steady state means we remove this d rho by dt and the dv by dt terms, which of course then changes the continuity equation to a situation where div v is equal to 0 and makes this first line of Navier-Stokes a little bit easier. The full project, which I'm not going to show you, involves two approaches, one of which is to solve for the velocity, and then the second of which I am going to show you, involves solving for the vorticity. So let's just briefly look at this. In the vorticity, we have the continuity equation, div v equals 0, and then the Navier-Stokes equation here. And notice that P has changed from a capital to a lowercase, it's still the pressure. As we know from electrostatics, you can solve div something equals 0 by setting the something equal to a curl. So we have what's called a stream function u, and v is equal to the curl of u. And so div of v, which is div of curl of u, is automatically equal to 0. Because we're in 2D with only x and y components, u is a pseudo-scalar. So it only has one component, so we only need to worry about that. And then there's another term we can look at, w, which is the vorticity, which is the curl of v. And Once you've done that, then you can come down to these two equations down here. So you have del squared u is equal to minus w, and you have del squared w is equal to something multiplied by w itself. If we then rewrite that, you see that we've got a very simple equation for u and a slightly more complex equation for w. But these are both elliptic equations. So we can use these in a concerted way to solve for u and w, which then gives us the velocity. So this is the project that we're dealing with. Essentially what we've got is we've got a set of equations we want to solve using some of the techniques we've developed in the computational physics course. And the obvious thing to do would just be to have a simple channel, but that's rather a boring problem. And so the suggestion, which I'm just going to scroll down to, is that we think about a channel with an obstruction in it. This is called a beam. It could be a block, whatever you want to do. In the original form, the suggestion was that the channel here is a river where you have salmon swimming upstream, so that's from the right side to the left stream against the flow. And these poor salmon get tired, and then the question is, if you're working for the fisheries agency, some kind of government agency who has to look after the fish, if you put a block in the river, will there be a sort of an area behind the block where the velocity of the fluid is decreased and therefore the salmon can rest? So that's what we're wanting to do, is we're wanting to solve the problem of fluid flow past a block and look at what happens behind the block. Fundamentally, the difficulty of this problem is setting up the boundary conditions, and they're given some boundary conditions here. I'm not going to go into this in any detail because really that's not what we're wanting to do. What I'm wanting to do is give you the background so that I can show you how I go about writing a report. What I'm going to do now is I'm going to show you the notebook that I created to do this. So we start off with boundary conditions here, and these are the boundary conditions we've set up for the block and the edges of the stream. It's a simple Python function on u and w. We then have a little bit of code where we set up the channel, so we set up the length and the width, we set up the maximum number of iterations and the grid spacing and various velocities, we put the beam in, and we create the initial values. The approach we use is successive over-relaxation, SOR. This is what we used for the Poisson equation, where you simply take the output from one iteration and put it back as the input to another, but you mix together the previous iterations. And so you can see that that's the kind of thing where we're doing. We're looping over points and we're combining things based on the equations, both for u and then for w. We then calculate a difference between the values at each point, and we iterate. And you can see here that we finished after 430 iterations with two various differences. We've set a tolerance there. The next stage is to visualize these differences. So this is just a plot of where u and w have been changing, and you can see here the block in the middle of the river. We're only doing half of the river, so that this should be then reflected back here on the left-hand side. Notice that u isn't really affected by the block. Now this doesn't really tell us anything, but it just does indicate that maybe this part of the channel is the bit where we're going to be having the biggest changes, and therefore might be the bit with problems. Of course, we're then going to look at how the successive over-relaxation converges. Here's the difference over time, rapid initial and then slow further. We can plot u and w, so we're plotting these both with IMSHO and, in the case of u, with contours. Again, we can see where the block is. W, remember, is the vorticity, so we might be thinking about something going on around the corner of the block. So now we create the velocity using a form of curl and plot it. And so, okay, so here's the input, here's the outlet, here's the block, and lo and behold, we get a vortex behind the blocks. More to the point, look at the color of the contours. It's very, very dark blue, so there's going to be very low fluid flow. So there's high fluid flow above the block and almost nothing behind it. We can plot that with either a stream plot like this or with a quiver plot. Again, notice with the quiver plot I'm actually zooming in on the vortex, and you can see that the length of the arrows is very small, which means that there's a low velocity, but it's actually, if you look carefully, going in a spiral, in a vortex, while the main part of the fluid flow goes along at the top of the channel. And we can also plot it using x, y, and then the magnitude. And again, you can see where the block is. You can see the low velocity behind the block. So that was a whistle-stop tour of the project that we've done. So now let's think about how we would go about writing it up. The temptation is to start at the beginning with the introduction because that's number one. But actually, I think sometimes that's not the right thing to do. Probably I would actually start with the methods. So in the methods, I would start by talking about vorticity. So I would actually go into the equations here. You could argue that might go into the methods. Either is fine. There is no fixed way of writing a report. I would also talk about methods for elliptical equations here, just again to give some background to what's going on here. You have to think about the level of the report. Who are you writing for? And in fact, I'm actually just going to put this as a suggestion at the top here, because the question who you're writing for will determine exactly what you put into your report. If you're writing for somebody who's about the same level as you, then you can assume the same background knowledge and you know how much you already know, ideally. If you're writing for someone who is maybe further advanced in their studies, then you might need to put less information in. If you're writing for somebody who is less advanced in studies, you might have to give more of a basic introduction. Under methods, it's important what you're doing here is in particular in this kind of situation where it's an assessment for a course, what you're doing is you're showing the assessor that you know what you've done. Okay, so the vorticity enables you to give the equations. The methods for elliptical equations is going to talk about successive over-relaxation, the importance of omega. You could put testing in here. And that's something which you could also put under results. That's a personal preference. So in fact, let me just stick in here also testing as a question mark, and I'll put a testing under there. So okay, we've now got a method section. So we've got vorticity, and we might want to change this. And now let me see if I can figure out how to change this. No, not that one. Here we are. Okay, I'm going to change this into a bullet point. So under the vorticity, I'm just going to note that I'm going to want equations, because that's going to show, this is U and W from V. That's just a note that we're going to need that in there. Under the results, okay, so we've got the testing. That's going to be something which shows that we understand the convergence of a simple and basic problem. We might want to talk about simply the free channel. It's a rather boring problem, and actually you might struggle to make something interesting out of that, but that's something that you could put in there. You could argue that's actually part of testing. We're certainly going to want to show the results for the block. We might want to talk about convergence, let's say testing omega, where omega, remember, for the successive over-relaxation is how much we mix together of the input and the output. And we might want to show something about vortices. And the reason that I'm just putting these very simple headings in is because this now allows us to see what's going on. We can see the basic flow. So under the introduction, we're obviously going to need a basic introduction to fluid flow, why it's important. We're going to need something about Navier-Stokes because that's the fundamental piece of information, and we might talk about the basic, the key approximations that we're putting in here. So we said it was 2D, we said it's steady state, and we say it's incompressible. So now we can actually start to see the overall shape of the report. We can see how the material is laid out, and at this stage you might even think, oh, hang on a second, I've got something in the wrong place. I think actually I'm going to take testing out of section 3 because I think that's a part of the methods. I'm going to leave that in section 2. I think, okay, the free channel, the block, the convergence, the vortices, we might decide actually to include convergence as part of the free channel and part of the block. I'm not sure. That would develop over time. Conclusions. Conclusions are something you write at the end, along with the introduction, actually, because once you know what the report contains, you then know how you need to introduce it. So conclusions, you could do something about the method. You could say that it's been applied successfully. It's a slightly weak conclusion, if I'm honest, but it's important to note that you can apply these techniques and still get a result. So you don't want to lean too hard on that. The block, this is important. Okay, so there's low velocity behind it. But you should also notice that there are vortices. Now, why have we separated those two? Why are we talking about that? Well, actually, think about it as if you were a fish. Okay, a little bit of light relief for you. So here's the stream flow. Here's the low velocity, but it may be low velocity, but there's still some kind of circulation. So maybe the fish is going to have to do something just to kind of stay still. So it might not be quite the ideal solution. And so by thinking about that, that's the kind of thing that you can put into the conclusion. You know, the way the problem was stated was, if you're wanting to provide an area for fish to rest, what happens if you put a block in the middle of the stream? And what you found is, yes, the velocity goes to zero or near zero, but there are then vortices. So those are pros and cons. So that's the kind of thing that you put in the conclusions after you've finished your analysis. So now we have an overall structure for our report. We have an introduction, we have methods, we have results, we have conclusions. Under each of those we have subsections, and then the next stage is to start putting in bullet points. So what I would say is, let's start doing single bullet points. Each bullet point needs to be short. It should be one sentence, one line, and it should give a key idea for a paragraph. So roughly speaking, what you're doing is you're now laying out the content of your report in a very, very condensed form, one bullet point per paragraph. When you come to write the longer form, you then know what's going into each paragraph. So fluids are used in many areas. So okay, that's far too long. So let's just say areas. What examples are there? Aerospace. Fluid flow over airplane wings. Oil, hopefully becoming less important as we transition to a green economy, but still necessary. In the UK, sewage is becoming quite an important area of fluid flow. This is the kind of thing you could just touch on. You don't have to give many examples or many references, but it's just setting the scene. This is why it's an important problem. So that's going to be one paragraph there. You could note the difficulty of solving the equations without necessarily specifying what the equation is, because the next subsection is talking about Navier-Stokes. Okay, so Navier-Stokes, we obviously want to give the overall equations. We want to explain the basic parameters, or the basic variables, the velocity and the density, and we note that they are insoluble. You might want to make a mention of the prize, something like that. And then, okay, so in our key approximations here, we would also say, a 2D system. We would talk about why steady state is an interesting problem. We would talk about what incompressibility means. Incompressibility, of course, means that the iti means that the density doesn't change. So that removes one complication. And in talking about these approximations in these paragraphs, you of course would also want to note the problems that those introduce. What are you doing in making that approximation? So I'm now going to remove that. So now we see. So I think it's actually really valuable to go through the report like this, step by step, section by section, subsection by subsection, and then putting in the paragraphs, making the paragraphs as short as possible. And then slowly building up the overall shape of the report. Once you've got the report shape at this stage, I would say you then start putting in figures, but at this point just use simple placeholder figures. So for instance, I might decide that I'm going to copy this. So I'm going to copy that image, and I'm going to pop back to my, oopsie, that's not what I meant to do. I'm going to pop back to my report, and I'm just going to pop in here, and I'm going to paste my image. Okay, it's a big old image. It's not particularly well formatted. I haven't put any labels on it, but it's there as a placeholder. Okay, I might decide to reduce the size just for now, just to make it a little bit more manageable. But then again, once you've started putting figures in, you can see how the argument of the report flows over time. Really, there's not much more that I can offer you at this point. So, what have we learned? We've learned that we don't want to worry about the formatting. Okay, you saw that I got myself tangled up. I can't remember how how to use this program, so I couldn't put in section headings. So I've just gone with an itemized list. We've seen that it's most important to go for the overall structure in the first place. Okay, so you want to get the basic idea of where the information is, what the information is, and how it flows. Think of writing a report as telling a story. You have to lead the reader along a path. You have to go from where they need to start, what they need to know, what you found, what that then means. And by using this kind of outline approach, that can help. Feel free to adapt things. There is nothing that says that a scientific report or a scientific paper has to be presented in a particular way. Some journals will force you to use particular forms, but overall you can generally think about how you want to lay something out. You know the material, you know what you've found, so it's up to you to think how best to present it. Once you've done a basic outline, start putting in the key ideas as bullet points, where each bullet point will, roughly speaking, correspond to a paragraph. That then again means you can see how the argument flows, how the material moves. Once you have an overall structure, once you have the subsections in, once you have the basic paragraphs in, you can start dropping in approximations to the figures. Then you can start writing. And I would say you should start writing on something simple like the methods. The methods are, they have to go in there, you know what you're doing, and it can feel really good to have written some paragraphs. After the methods, I would then move to the results personally. Once you've got the methods and the results there, then you can write the introduction because you know what the reader needs to know, and you can write the conclusion because you know what you've found. Don't feel like you have to write in a linear way. You can fill bits in as you go. Don't write in a narrative way. Don't start by saying, in this project, I started by looking at this problem. That's narrative, and it's not really what we're wanting here. What we're wanting here is a report that tells us what you found, not how you found it. I don't think there's much point in putting this up on the web, this particular document, because it's very rough, but you can see what it looks like here in the video. So I hope that you found that helpful, and good luck in writing your reports.